happy to sort of do it before this man, whom I had as a teacher. He's this Maurice Lévy, who was one of the persons who sort of resurrected French physics from the ashes where it was buried even before the war. That's not even due to the war. It was actually coming from before. Anyway, so what's happening is that it's a school. Most of you are mathematicians. My affiliation says that I'm a physicist. Sorry, nobody's perfect. So, which means that I speak a language which might be a bit different from yours. On the, what questions, where I'm asking the questions, may be a bit different from the way you would be asking them. So please don't let me mumble. I count on you to sort of, whenever there is something which is fishy or funny or incomprehensible, you raise your hands and don't let me go off. Okay, so what is it about? So this title, so actually I sort of took some old presentation of mine, it doesn't really matter. I'll try to sort of walk you through a number of things that are of interest to us and hopefully to you. So that's sort of the sort of things that actually was mentioned yesterday was this question of intermittency. So by that, what do I mean? And what are we talking about? So I'm showing here on these two figures some records of the effectively the velocity gradient square as a function of time or space. Details are immaterial here, and it's normalized to the mean. So that signal here that you see has a mean at 1, which is I'm shearing. Okay, which is sort of down here or down here. So what obviously the structure of the thing is that it's not at all gently fluctuating around 1, but it's brutally jumping from not very much to some very large value. So here now goes like 20, like to values like 60-ish. What's the difference between the two flows? What's what you'd call a Reynolds number. So in a way, that one is less turbulent than this one. So the sort of what it shows is that what it suggests and implies is that this phenomenon of having gradients which are very small and jumps to huge values is getting worse as you take a flow which is more and more turbulent or has a higher and higher Reynolds number. So that's what I will refer loosely as intermittency. So maybe there's some issue about how you define these things, but in my case, that's the way it is. So, okay, so I was showing that velocity gradient can sort of jump to high values. So, what is the story? So, there are in fact two concepts which are sort of tied together. The first one is what some people would call the zeroth law of turbulence. Which is something that probably engineers knew, 5 centuries ago before anybody knew what was viscosity. So the concept is that if you sort of take some fluid and you start stirring it, and you have viscosity very small, you might infer that dissipation is very small, and therefore there'll be no dissipation. And the answer is wrong, dead wrong. What's happening is that instead, even if the viscosity is very small, you still have some finite dissipation. So is that clear to anyone what this thing is? Yeah, no, but that's okay. So it's just saying that here, on the left-hand side, there's just so you just write budget of energy for the Navier-Stokes equation, and you have this term here, which comes for the dissipation. Okay, and so the statement that it's independent of nu when nu goes to 0 means that, there is some sort of a constant, and this constant is effectively coming from the large scale. So you effectively store your flow at large scales, and you have some dissipation, and the dissipation doesn't care about viscosity. Well, it cares that it's there, but once it's there, it doesn't matter how small it is. So you have this quantity which is constant, and when you sort of put things together, when you have this velocity gradient, effectively varies like epsilon over nu on putting two things together. So velocity gradients, so they will typically scale as this quantity here, which is built on the large scales, and there is some Reynolds number here. So as Reynolds number increases, the velocity gradients on the mean increase. Very good. But that's not what I was showing before, because I had sort of conveniently divided by the mean. So what I was actually showing was that it was not, well, I was not saying anything about the mean, but in addition, the largest value of the gradient, they grow with Reynolds much faster than the mean. And that's what this previous picture was showing, and that was effectively the notion of intermittency. And well, so the question, which some people would say is a $1 million question, is that how can large velocity gradient be generated in the bulk? Away from boundaries. Of course, there are boundaries, which is another kind of worms, but here I'll just be focusing on what's happening in the bulk, so away from any boundaries. The $1 million question, of course, is an allusion to the Clay Foundation riddle. Okay, so what am I implying here is that there is effectively a mechanism whereby velocity gradients can be amplified. Right, so you have Navier-Stokes equation, du dt plus u grad u equal minus grad p plus da da da. It goes with gradient amplification. The way you do it is, for example, by writing the equation of evolution for vorticity, curl of u. All right, so that sort of goes with an advectionic part, u d plus u grad u d by dt plus u grad omega. There is this sort of a form which you would have expected without thinking too hard, which is just viscosity dissipation. And there is this tidbit here. So that's the one which is interesting. So that's what people call vortex stretching. So effectively, you can rewrite, well, one classical way to rewrite that term here as a product of vorticity times the rate of strain. Rate of strain, I can write it up if you're not familiar with it. So that's just the symmetric part of the velocity gradient. That's the sort of a deformation, and that what you attributed to Helmholtz, which I didn't know decomposition. So that was the sort of a part of the flow which sort of tends to deform a quantity. So effectively, the thing is saying that vorticity will be amplified, or well, potentially this rate of strain can do something to vorticity. And in fact, it's, when I say here, it's sort of known, so if you open up an engineering textbook on turbulence, it will tell you that this guy is very important. This sort of vortex stretching is important. And in fact, it is positive. So it means that it sort of does contribute to amplifying vorticity. So that's not a joke. So it's really happening. And then there are some sort of justification for that. There is this also, okay, so I know you're a mathematician and you guys are going to laugh at me, but nonetheless, so the notion here, as ridiculous as it may be as it may sound, so if you look at it, that's a very superficial way. So you have the omega dt, so which is this sort of advection equation. So it's a product of rate of strain times vorticity. Now, okay, very crudely, that in both cases, for S and for omega, these are both velocity gradients, right? So of course, they are sort of a very different status, but if you're sort of very naive, you say, well, at the end of the day, that was just, you're just multiplying velocity gradient by another velocity gradient, and you end up with an equation which is, with a thumb, which is d omega dt equal omega square, which it won't take you more than 2 minutes to solve this equation and to show that there is amplification to infinity. Now, of course, it's a joke, and sort of made it clear that no one believes that what I just said, because S and this equation in a way is deceivingly simple. So it just says that well, there is S, there is omega, both are related. I didn't tell you how they're related, and that's where the rub is. But I'll come to that. But anyway, so the difficulty here and the danger is that we are facing some quadratic mechanism of amplification in terms of the gradients. Okay, so good. So that's sort of setting the stage. So another tidbit of information that I will give is what sort of a flow are we thinking of? So one of the way to sort of address these problems of high Reynolds number flow / turbulence is to think of what is called homogeneous isotropic turbulence. Is sort of in plain English, what it means is that isotropy, you sort of make the explicit assumption that the fluctuations are invariant under any rotation. So there is some sort of SO3 symmetry which is floating around, and whether you're looking at the flow like this or like that makes no difference. So that's isotropy. And homogeneity, well, as you'd expect, doesn't matter whether you're here or you're here, or sitting at your stage, the flow properties will be the same no matter what. So that's obvious. So and that was it was not invented by me, so it was some sort of old story. It was invented by the ancient giants of the mid 20th century. So G.I. Taylor, with some further development by von Karman, Haworth in 38, Kolmogorov, and on and on and on. So that's sort of effectively, these people forged the concept and sort of say, well, no, look, if you want to look at these fluctuations and try to have some nice statistical description, let's take the simplest possible setup. Here you go. That's the simplest possible setup. Okay, so now, of course, you may laugh because think of any turbulent flow that you'll be generating. It will not be homogeneous isotropic unless you're making some sort of extremely delicate effort to sort of make it like that. Anything you're doing, well, you have a flow passing by your car, your plane, or you're stirring a bucket of fluid by sort of you're just pulling it like that. It's not going to be isotropic. Sorry. So this notion being that what we're doing is we are sort of studying things which are very anisotropic by the way they are being generated. However, so the expectation is that think of your bucket, right? So you're stirring it, and it's turbulent. You need to generate these sort of large gradients. So it means that the gradients are not based on the size of your system, but based on much smaller scales, right? So the statement that my velocity gradient is U over L, large scale, squared divided by times Reynolds, means that, in fact, there is some sort of a scale happening at a much lower scale. So there is effectively, the notion here is that if you have some turbulent flow, there will not be one scale, the large scale, but there will be all sorts of scales being forced between the large scale where you've been forcing and some hypothetical dissipation scale. And so the notion is that, sure, the flow at the very largest scale is completely anisotropic, completely crazy. I mean, so this homogeneous isotropic turbulence thing is completely ridiculous. However, when you sort of go down to smaller scales, chances are that things will become isotropic. So in other words, as you sort of look at the finer and finer scale, they will not remember who was generating them and sort of become more isotropic. So that's effectively the underlying assumption that was more or less, that was sort of very clearly written by these sort of great people who sort of understood that, of course, the flows that an engineer is facing has to cope with has nothing to do with that. Okay, so so there is one part which I will not mention, but of course, so being a physicist, I'm sort of close to experimentalist. So doing it experimentally is possible. It's hard. So you have also to sort of address all the questions that I've been saying. How do you sort of make sure that the flow you're looking at is really isotropic, homogeneous, etc. Not simple, but so there is some discussions that you can have. And but they sort of here that I will be using the fact that that's a great setup for doing simulation. So by that, what is meant is that you take a system and you write down Navier-Stokes equation in there, and put it on the computer and turn the crank and solve. So that's effectively what I will be. I will be heavily using that sort of thing. Okay, so that's effectively the cast. So with all sort of various parts which I will try to sort of arrange for you. Okay, so if you want to do this, okay, so if you want to study this kind of flows, you want to push and look at gradients which are as high as possible and even bigger, well, you, of course, have to be careful about what you're doing. The reason being that, well, what is a large velocity gradient? That's a large velocity difference over a small distance. So math 101, I mean, you're just a 10th grade or something. Or equivalently, that's 1 over a time scale. Right. So if you want to do it right, you have to sort of make sure that the small distance that the system wants to reach are effectively properly resolved by your simulation, and also that the smallest possible time, which are implied by the large velocity gradients, are also properly resolved. So there is both a condition on size, on the mesh size, on time scale. And so, I was also mumbling probably at the beginning that what we are looking at are rare events. So then rare events immediately rings the bell that, hey, if you want to do something, say something significant, well, you have to sort of make sure that you have enough of them to sort of say something which is meaningful from a statistical point of view. Which, so all the things, lo and behold, means that there's a cost. So, you have to sort of put, enough grid points, smaller enough timescales, and run for long enough to have enough, well, to be able to say something significant. So there are a number of things here. If you want, come to me afterwards. But I will skip all the gory details about what we do. So suffice it to say that we think we are correctly resolved. Okay, so and that's so ignore that part. That was sort of explaining the transparencies that I just skipped. But so it's effectively we have a bunch of runs with pretty high resolution. So from 1024, which is nowadays is relatively doable. That one gets pretty harsh. That one even worse. And so we have okay. So this resolution here. This one is probably an overkill, so we probably did it too much. But I mean, in a way, we did it on purpose because we didn't quite know where we're going, so we sort of exaggerated. So this one is probably on the sort of low side of what's acceptable. On that sort of the amount of time we have, number of simulations enough snapshots that we've analyzed. So okay, yeah. Number of fields. Okay, number of fields. So what we do is that so we effectively stop the simulation, dump the field to some file, and then return to the file and do the analysis on so many files. So that's so that's the number of things that we have. Okay. Yes, that's not a bad number. So what we do, of course, we sort of estimate the error we're making, the level of fluctuation. We estimate the error bars, and if the error bars are too large, we're not showing it. So we just show what we have out of that. Give me 10 times more, I'll be happy. 10 times happier. Well, square root of 10 times happier. Higher numbers of okay, so okay, I'm sorry. Yes. So what's so you see? So this is Reynolds number. So there's some square root. There's some immaterial square root factor and some factor 15. And God knows. So it's effectively here. I'm just sort of increasing Reynolds. Stated otherwise, I'm taking my system. I'm lowering viscosity. And I'm lowering viscosity here, so you see, so that's sort of velocity 1, sort of well, not quite 2, but each time I sort of go down, and I go down until my system can't take it anymore with so many points. So the exercise, the slides that I skipped was just to sort of explain what is a resolution? So once you give me the sort of the mesh size, how far I can go with appropriate resolution. So that's effectively this connection here was the slide that I was showing. So it's saying that and if you want to go higher, you pay the price. All right. The idea was it? Okay. Yes.
What kind of statistics do you impose on the samples of your initial data?
We just run it. It's okay. So yeah. It's forced, so the thing is not, so there is a forcing term. So, in the equation, in the Navier-Stokes equation, you add plus f, plus some forcing term of sorts. So that's sort of a story, people have checked that effectively all forcing terms do the same. So, that was checked at low res, at low Reynolds. So effectively, we sort of reach some steady state, and we sort of look in the steady state. Right, so they sort of start constructing statistics once we've reached a steady state. We're not doing some initial value problem. We are, but ultimately we are sort of putting ourselves in a statistically steady state. And again, so that's all sorts of people have all sorts of different schemes. There is no serious discrepancy between us, as far as I can tell. So statistics is tough. So, maybe that, there would be some number, so 50 digits, there would be differences. But, sort of the bulk, the ballpark is fine. Okay, so what are we, okay, so what intermittency? So, okay, the first thing is that, so there is this question which have been very well introduced by my previous, my predecessors, yesterday. So what is the spatial structure of strain and vorticity? So here's my box, fair bit of it. So by this sort of a cyan thing, I'm representing values of omega, capital omega, which is the vorticity square, so it's entropy, if you wish. And so that's a cyan. And so it's 2 trace of a square, and that's red. And so that's what effectively you have. So that's the units of length are measured in this eta, which I've not introduced, but never mind. It's just some length. Suffice it to say that it's a good length to consider these kind of flows. And the threshold here is 25. So it's actually divided by so it's just quantity which are normalized. So the quantities I'm showing are effectively the surfaces where the values of entropy, cyan, or strain square, red, exceed or reach here 25. So it's sort of all over the place. It's a bit of a mess. You start seeing vaguely there's this sort of a bit of filament structure, not very clearly, but you vaguely see them. So when I go from here to here, what I've done is simply zoomed in. So actually there is one point in the center, which is a point where there's something very intense, and I'm just zooming in, right? So here, 2000, here 600, so 25, that's the same threshold, and here I increase the threshold by 2. So that sort of course gets rid of some of the stuff. You sort of see less. And then I keep blowing it up by 150. So again, same threshold as this one, same threshold as this one. So threshold still increased. And then you start seeing that, the flow is getting a little bit simpler. There are manifestly these sort of tubish kind of structures here. Which are, these sort of, this look like tube, I'd say. patience. The tubes. The final one is that one. So that's effectively what you sort of zoom in, and so that's even smaller. Now I'm 500 times larger than the mean, and then I'm zooming still further in on the 1500. So that's effectively what these guys are. Yeah. Okay, so my delta x was on that one it was 2 points per eta. So there are 50 points, 50, 50. So so that one, and I'll show. Well, if time permitting, I'll show something more. It's well, again, it's not great. I mean, I had more, I wouldn't be unhappy, but it's pretty reasonable. Okay, so on that, okay, fine. So that's what it is. So it is something that people have known. So in a way, I'm sort of connecting up with some long story. People have known that in the simulation there are these tubes floating around. There was on this previous one, I was mentioning that the first one was so it was Ericsigia, but it was with a computer that was much smaller than that one, right? So it was on the Cray one, and it was the stunts you had to do to see anything was unbelievable. So there's been sort of a continuation of that with a number of great papers which I've not listed, but so we're just there. So that's sort of a connection with my experimental colleagues in Göttingen. So when he saw that one, Eberhard sort of immediately noticed, but hey, we also saw it in the experiments back at long ago, by sort of having this sort of little cavitation bubble which can migrate in the region which have low pressure, and therefore which provide you a way of visualizing the sort of most intense vortex tubes, if you wish, in the flow. Well, actually lowest pressure, which you can plausibly relate to highest intense vortex tube. So that's what it is. So in a way, it's not what I'm showing you is not just some sort of a crazy numerical person imagination, but it's something to do with the flow. Okay, so. Now, what this notion that these guys omega entropy or strain are having larger and larger fluctuations once normalized. So this omega tau k square is effectively omega divided by the omega average. So that's what it is. So that quantity here. If you calculate the mean of this quantity with this histogram, this PDF, you'll find 1. That's the mean of that is 1. And then, of course, the interesting thing is that the thing extends to, as advertised, insanely large values. So for vorticity, you get 10,000-ish. For strain, you get actually a little bit less, for factor of 2. Roughly speaking, less. But so these things extend further and further. Yes, color code shows you that when you go from low to high Reynolds, these sort of tails will whoosh, increase like mad. So again, which is what intermittency is about. I mean, yeah. No, it's just the fact. No, it's just saying that for a quantity whose average is 1, the thing extends to value. You reach values which are 10,000 or something, or extremely large. That's just no. Yeah, there's the horizontal axis, and the thing sort of fans out when Reynolds increases. Whoosh, the thing sort of extends further and further out. In a way, it's not. Some people would have said, well, yeah, we know. Okay, this sort of a vague surprise will come later. But yeah, so in a way, so that's just the first statement that was on my first transparency, that as Reynolds increases, you see more and more of these high fluctuations. That's all. Go ahead. Please do. Probability density function. That's an histogram. Sorry, yeah, the jargon. You know, put histograms. That's yeah, sorry. And actually, yeah, I keep. I know the D. I also keep making mistakes. But yeah, histogram. Yeah, that's what it is. Yeah. Okay. And so yeah. So another remark that I'm sort of smuggling in here is that so you know you have these vortex tubes, right? And they're pretty intense. You know, a vortex tube. So you know, think of Renzo's presentation yesterday. So you know, it means that you know you have some flow which is going around some axis. The sort of a relevant question is what is the velocity difference from you go from one, so that you'll have some vortices, some velocities that will go up, go down. So and you cut across. What will be the velocity difference between the highest up and the lowest, no, the highest down? Well, that's effectively what this guy is showing. And what it shows here is that when you measure your velocity, the difference, and you normalize by the RMS. So as much as you get, because the flow has some RMS, and velocity fluctuation are of the order of RMS, not much bigger. Root mean square? Oh God, sorry. Where's the question? Yeah. So sorry. Yes. So you're not statistician, guys. But, you know, so you know, no, fine. You know, you have a signal, and you just measure the fluctuation of the U square. So U is 0 on average. You look at U square on the average of U square on the square root of that. So that gives you this sort of measure of the velocity. And that one, contrary to these insane velocity gradients, is actually pretty Gaussian-ish. So you know that one doesn't have these sort of insane fluctuations. That's sort of much more. If you look at the histograms, it's sort of much more bounded. I mean, much like you'd have for Gaussian. So the statement here is that the velocity difference across anything. So and that one is done at a length which is pretty small. And so here the statement is that over a very, very small scales, you have velocity difference which are order of the velocity in the flow. So these little things are effectively accumulating all the velocity difference there can be on a scale which is extremely small. So that's effectively the point I wanted to try to make. Okay, so yeah, so fine. So now, some little things that we notice which are of vague interest. Okay, so remember, I was showing you a minute ago this this PDF for different Reynolds number and for either the strain and vorticity. So that's the same data. Okay, so obviously there's a rub. I'm hiding something, and what I'm hiding is this. So effectively, instead of normalizing it, I'm sort of dividing it by the mean, I divided them by some other time scale. So some higher value of the mean. And so the way we did it was effectively to sort of say, well, you know, there is effectively some typical value of these guys for the mean, because the mean is the mean is the mean. But for these sort of large crazy events, there is, well, that's some sort of act of faith. There is possibly some other time scale or some sort of a different magnitude, which we relate to the mean by some function of Reynolds, roughly speaking, a parallel of the Reynolds number. And so here, that's what we have. So that's curve fitting, effectively. So we just sort of take our data and try to sort of superimpose on that's what you get. So in other words, here the statement would be that the things which are, which are extended further and further in some sort of no particular, well, there is some law, but of extension of these PDF. So that would sort of effectively be a way of capturing how these sort of PDF are extending as Reynolds increases. Yeah, so, okay. So some more systematic way. So effectively what it means is that if you look at this function here, the functional form of these guys is pretty much a stretch exponential. So p of x goes like exponential minus x to some power c less than 1. So another thing which sort of gives you in this sort of a lean log representation. So if it were exponential, that would go like a straight line. And if there is this stretch exponential, it gives you this concavity, which effectively reflects this. So effectively, so what we do, we can sort of fit the form by such a functional form with a value of c, which is approximately 1/4. So we don't quite know the value. So effectively, we did a few values of c around 1/4. So it's 1/4, a little bit less, a little bit more. So we fit systematically, which sort of gives some pretty good fit, and then we sort of measure that quantity here, which sort of tells you how far will the PDF, what will the tails of the distribution extend. And so effectively, so we have, if you take this b to 1/c, which is here, and massage it a bit, so you see effectively some law here, which is effectively consistent with what I was showing, which is roughly like a power law here as a function of Reynolds. Okay. So that's good. And the last, okay, so but in a way it's descriptive, right? Well, I mean, okay, it's descriptive one way or the other. So the other observation, that I would like to sort of show you is that you may ask, what is the strain acting on vorticity, right? If you think of what I was one of my first transparency, where I was telling you, well, there is this amplification by strain. It is not a bad idea to ask yourself, what will be the strain acting on a large vorticity? So what we do here is that we condition here, that one, strain on vorticity, and sort of, make it dimensionless. And so these are the full lines here. And so what you see is that effectively there is some growth. So when omega grows, the strain increases, but it increases slower than omega. Remember, so at some point say, well, let's be naive and say that all these guys are the same dimension, same growth, etc. No. Here, what it's showing is that effectively the strain on a region of very intense vorticity actually grows slower, typically with a power law gamma, where gamma is less than 1, and so here are some sort of measurements of gamma. So the thing sort of increases from 0.6 to 0.8 or something like that. So then of course, what else can do? You fit, etc. So that's sort of a representation of the things that we have here. Okay, so that's so this sort of a possible rescaling of the velocity of the histograms of vorticity strain on this sort of a law of this growth of sigma on omega. So they are sort of effectively this sort of a two. Well, this one's surprising, I'd say. That was not. Well, that's us mostly, which I'm showing here. Incidentally, notice that the other one, if you condition omega on strain, that one actually sort of grows with the power 1. So that one grows in a much less surprising manner. But this one is the one that sort of behaves in an unexpected way. Okay, so let me try sort of pull things together, right? So I sort of took my hat, pulled a rabbit, pulled another rabbit, let them together. Yes?
Do you mean that, in some sense, strain is not the main contributor for the growth of ants?
It is. I have no choice. I mean, that's the equation I wrote was that d omega dt equal s omega. That's there's nothing to argue. That's just part of life. That's in the equation. So vorticity, so strain is the way vorticity grows. However, strain doesn't quite behave as naively as I was implying or suggesting in one of my first transparencies. Which is normal because strain has a life on its own, which is not So I wrote the equation for vorticity. Write down for fun the equation for strain. It's not the same. not at all the same. So, there is some other growth mechanism. I'm sort of cutting a story short, a complicated story short here, because I'm just showing S omega and pretending that, I'm discovering about S. Well, I should do S and omega simultaneously, which I'm not doing here. So, but at the end of the day, d omega dt equal S omega, you have no choice. That's part of life. Okay. Okay, so like I said, so I'm just trying to reconcile the two rabbits that I pulled out of my hair, of my hat. Okay, so let's go back to elementary fluid mechanics. Okay, so there is this these sort of things that is in any textbooks on fluid mechanics, which is called Berger's vortex. So what is it? So you just take a vortex and you imagine that it's been strained by a simple strain field like that. So which is axis symmetric. So the sort of the tube would be in Z, and you assume that your strain is axis symmetric. So along this Z doesn't matter which direction you're looking, and it's sort of strain it like this. So you whoosh, try to strain it. So there is this, but it's so we're doing real fluid we're putting some proper viscosity, and so when you look at the solution, you sort of calculate everything. So you find that the radius of this tube effectively scales as the viscosity divided by the amplitude of strain to the half power. Which you can solve. You can also sort of say, well, what can it be dimensionally? Here it goes. I mean, that's just what it can be. So that's what it is. Here there is nothing. It's just a solution, fact. So then we ask ourselves, well, I guess which is probably was the question that you were implying. What will be the strain acting on an intense vortex of intensity omega? Well, of course, we don't know that. But so we have this funny observation that the strain here condition on some large vorticity has this sort of a functional form. And so what I will pretend effectively is that if I want to calculate the size of a vortex acting the flow, I'll just use this formula and take the value of sigma given as such. Okay. Right. So that's effectively omega square. That's the average of, that's a Kolmogorov time, which is 1 over vorticity square. So that's effectively, I'm sorry, that one I sort of I swept under the rug, but so that's effectively the time scale that you have in the problem, sort of smallest time scale that you may have. So and when you do that, well, you can start doing back of the envelope calculations. That's all there is, and effectively estimate the size of an intense vortex of intensity omega. And that's what you find. So there is this sort of here says that we check that in a way. So in some sort of no, of course it's not direct way, but some sort of indirect way, which is effectively. So you take a vortex of size omega, and you ask yourself on what scale has it, so the notion being that. The most intense vortices will be shorter. Would have some sort of a smallest size, smallest radius. This is okay. So this notion here. So you have this guy here, and so there is this one, and there will be this. So that's what effectively what I'm doing. That's what this formula is trying to describe. Of the distribution. So there is a distribution of vorticity and there is a characteristic length, and that's the characteristic length. That's what comes from this analysis. Go ahead, please. Okay, so and then so with that you can effectively close the problem, because once you said that the velocity difference across very intense tube is u prime, then effectively this omega, then you start self-consisting what you wrote, saying that omega will be effectively of the order of the velocity scale of velocity divided by the scale. And effectively you can close, and you start effectively writing an equation for this tau x, which will involve this gamma. So this tau x that I was writing will be effectively something like that. So there is effectively, so there was some almost power law in what I was showing, and there's a power law in gamma, and effectively, so the two are connected by this, and that works effectively extremely well. So yeah, I'll well, okay, yeah, so that's one we're pretty okay, because so it's okay, right? So that okay, that works. I'll skip the detail. If you're interested, you'll just come back to me and ask me. Okay, so yeah, so I guess now I have 5 more minutes or something, maybe 10, not much more. Maybe 10, okay. Yeah, okay. So I'll walk you through relatively quickly. So the important, okay, so what I've shown is that crucial in this business is the strain, right? I mean, the strain, and if you understand the strain, then you're the king. I mean, you sort of, you can do all sorts of things. So the notion here was that, well, can we fool around with the strain and understand it better? There was this sort of notion that, there's Biot savoir kicking in. So what you can do, of course, if you have vorticity, you can write the strain as a Biot savoir integral, right? So you express as omega, and well, then you start hitting with the differential with d by di, d by dj, etc., and that's what you find. So the strain is expressed as some Biot savoir, well, Biot savoir-ish. That's not the classical one that you have in electromagnetism books, but it's some sort of little cousin, very simply related. And then, so okay, so that's what we have. And in principle, when we have vorticity, well, strain, here you have it. But this sort of notion we say, well, let's sort of try to understand a bit what was going on. So what we did was say, well, if we take a point, so there's this sort of zoo of vorticity, and we're asking ourselves, well, what will be the strain which is due to points around you within a ball of size r, and what would be non-local, which we say is coming from the rest of space. So integral over the rest, r greater than capital R. So that of course obviously depends on a distance r, some sort of cutoff distance that we want. So well, okay, so there is some little game. It's actually not very simple to, well, I mean, okay, it's simple once you know how to do it as usual. But okay, fine. So there are some tricks to sort of do it efficiently, which is, okay, so well, the people have sort of written some sort of a crazy series on that you can resolve pretty easily. So what we do is the following. So now that's pretty much the sort of monsters that I was showing, this sort of a case where you had some insanely large value of vorticity. And I'm asking myself, well, we're asking ourselves, what is the strain locally induced locally, and what is the strain coming from elsewhere? So here I'm showing, these sort of things that I showed before, and here it's a cut through this plane here in the middle. And so you see that's the most intense region, and that's some sort of this little satellite around here. Again, so insofar as resolution is concerned, I mean, that's, I've seen worse. And so here we calculate the local strain at a size which is effectively of the order of the size of the vortices. And so what we find, is that, much to our surprise, is that the local strain is actually contributing not to amplify, but to compress. So it sort of corresponds to this production term of vorticity by the local strain, which turns out to be negative. So, so you can do it systematically. Of course, I show it on a particular example. So when you sort of do it systematically, you see that it's always the same, with actually massively the same. Why would that be of any interest for PD people sort of hunting for large events? This sort of insanely large contribution. I'll just okay, I forgot. Yeah, I don't know whether it's properly written. So there are sort of a work by Constantine and company, which effectively tell you that there shall not be any blow up until the quantity I was looking at becomes infinite itself, but at the minimum positive. There has to be, in order to have blow up, you need to have enough stretching generated locally. You just don't want the stretching to come from elsewhere, because then it's passive and there's nothing happening. So you need to have some internal stretching. And that, the lesson here is that this internal stretching is not that there. It's just not there. So you forget it. So insofar as the solutions that we generate on the computer, we find. There is no hint of any sort that they will do anything crazy. They're just sort of effectively the sort of fuel to sort of grow up to an infinite region is just not there. Okay, so I'll just effectively sort of close what I wanted to say here. Okay, so where's my mouse? Okay, yeah. I'll just do it quick. Yeah. So that would effectively. So there was some sort of a half-baked slice of a conclusion, which I was I would not, and so my temptation was actually not to stop with that, but because there is this question about reconnections and interaction of vortices, I wanted to sort of show a little video which is kind of cool. Well, which I find cool. Up to you to decide. I'll show it, and if you want to ask a question or watch it, you do whatever you want. So that's